Record. All right, so I'll just quickly take this in English. So this first version will be in Swedish because the attendees are all Swedish today. And then I'm going to switch and record an English version after this. All right, så på tal om det, höll jag på att säga, så kan jag ju passa på att tipsa om i LISAM så finns det väldigt mycket material om SweetCap i olika former. Så att gå in på de där sidorna då. Om ni inte har gjort det redan så finns det referensdokument 2021 reference documents. Och sen har ni massor om SweetCap och annat här och filterdesign också som ju bara go wild här i någon lämplig pdf-läsare. Så har ni i princip allt, eller ni har allt ni behöver för labbprojektet då. Och sen så finns även en version som förklarar SweetCap utförligt i en 25-sidig pdf här också som är bra att gå igenom. Det finns också då förslag på hur man kan analysera om man har offset-fel som ni behöver göra. Och gain-fel och lite sånt på de här opamparna eller förstärkarna. Okay, so yeah, welcome. We started in Swedish a bit, so I'm going to switch to English. I just had a very quick introduction to the material that you can find in the LISAM folders. So once again, just course documents, 2021 reference documents, filters, etc., etc. There are quite a few, maybe even too many PDFs, but please browse there to find information on how you're going to prepare your filters for the last lab, for the last part of the project. Today we're going to focus on this type of filter, so we're going to take a little trip towards this. This is a continuous time step ladder filter. It has some nice properties. It's shown to be optimum, in fact, as a function of variations in the parameters. So that's why we use that as a reference filter and then implement these components with our switched capacitor accumulators instead. And since we've chosen a reference filter which is optimum, we also then choose corresponding SweetCap implementation which is optimum, or near optimum at least. All right, yeah, and then we're essentially going to do the steps which you hardly can see in the camera at the moment, but we're going to do a sort of trip from a reference filter, include some signal flow charts, do some manipulations, explain those manipulations, and then boil down to the implementation with 3 switch capacitor accumulators here. And that's the filter you're going to simulate in the lab and the project. And then we're going to look at some ways to find the values and do some potentially slight modifications. So that's where we're going to land today. And then we have a session on Tuesday, a 4-hour session, theoretical part where we can discuss this further. So that's the suggestion for that for Tuesday to prepare some questions essentially for lab 2 and 3. Okay, so let's bring this down and then start with the basics. So last time we looked at the accumulator, and essentially we had a circuit looking something like this, and there were some different options. We'll come to those shortly. Something like this. An operational amplifier and the capacitor. So that's the op-amp you have designed then in lab 1 that you're going to use later. And then on lab 2, you will simulate this type of accumulator, not exactly this type, but one type of discrete time accumulator. There were some options here with respect to the switches. You see we have 2 switches, so we can sort of place them in phase or counter phase. So dependent on that action, I can form a delay And the delay in the discrete time world is also similar to phase shift if we have a sort of transient signal. If we did the analysis on this one, we did the charge redistribution analysis, and we spent quite some time last time, and I suggest that you practice a bit, but essentially it's quite simple. We have two phases, so we have to note down the states of those two phases, the total charge on each of these caps. We introduced some reference directions like this. Those you choose yourself, but the idea with choosing the reference directions is that it's much simpler to see where the charge goes once we flip the switches back and forth. So we have two phases, and then we have three transitions. We have to this phase, to the other phase, and back to the original phase. So we have to investigate these three cases. And that simply gives us a set of equations, which is really not rocket science per se. It's quite simple difference equations. Then if we do that, we come to the conclusion that if this is VO, this is V1, we get the discrete time relation, V2 of Z divided by V1 of Z equal to the minus C1 divided by C2 times 1 to the 1 minus Z minus 1. That's a standard equation or transfer function in the Laplace, in the discrete Laplace transform, the Z transform of an accumulator, an integrator, something that adds and multiplies on top of itself. So if I would add, something like a DC, or like a number 1, I would get 1, 2, 3, 4, 5, 6, etc. multiplied with this C1, C2, something like that. We could, last time I had made a slight mistake in one of the slides. The other one was correct. But if we look in the discrete time domain, for the Z transform, we have the boundary for stability on the unit circle. And that's where Z is equal to e to the j omega t. And omega is my frequency variable, and t is my sample period. And in the discrete time domain, one sometimes refers to omega t as capital omega also. So that's a variable between 0 and 2 pi, more or less. Okay. And then we said that if we want to map or compare this with a continuous time domain, so this is my discrete time, this is my continuous time, I would then have a certain range on my axis, which is sort of valid. And one validity, of course, is the sample theorem. So it doesn't make sense to have a frequency axis here which is more than half the sample frequency. So this entire span on my omega axis here is equal to the sample frequency. So this point here on the unit circle corresponds to the sample, half the sample frequency on the edges here. And we also quickly discussed that this is a discrete time function. So if I would take an oscilloscope and measure on the output here, I would obviously get steps. Either it might be track and hold, or it might be just hold. But for sake of discussions, we say that the output looks something like this. So it's a stepwise function where we increment every t, etc. in the time domain. So this will be V0 of t. And if I would look in the frequency domain, we said last time, if I would take the continuous time frequency spectrum of this type of signal, I would typically have the sync-weighted structure, which has zeros at multiples of the sample frequency. And then dependent on if we look at the structure here, we concluded a little bit like there is a certain frequency range where it makes sense to represent your signal. So I mean, I have my voltage here, my signal coming into my accumulator, and I don't want to destroy this signal. So first of all, I obviously have to meet the Nyquist theorem, which means that I have to sample faster than twice the bandwidth of the signal that comes in here. So that's one argument. So I definitely need my frequency to be within this range, up to fs half. But I also have to take into consideration that something is happening with the spectrum here. I lose some dBs. I actually sort of distort my signal. So for that sake of argument, we typically said that we want to limit ourselves to an even narrower band here, where the signal is not distorted that much. So typically we have that f bandwidth must be much, much less than the sample frequency. So not only Nyquist, but also this. So one could argue that this is a bad requirement for SWIT-cap, but remember we can probably switch the switches today quite fast, and also the op-amps we can do quite quick with high bandwidth. You have 500 megahertz bandwidth in your lab 1. And again, we have the improvement over this typical continuous time integrator is that we don't need a resistor. So that's the benefit we have. All right, so just to sort of conclude that is that if we compare the discrete time unit circle with the continuous time axis, y-axis or omega axis, the imaginary part, we typically limit ourselves to a certain narrow angle here. So we typically have something like omega t, this guy, being less than a certain small angle here, which sort of relates to this width divided by the whole width here. Numbers we can't really tell, that depends on the spec per se, but a small number. And that means that this part of the unit circle then maps onto a certain part of the omega axis like this. So we're going to look at this shortly when we talk about the filter design, because we do have two variables here. We have omega and t. So I can choose to increase my sample frequency, for example. Then this angle will become more narrow in this world, but obviously doesn't change in this world. It's still a certain frequency in my continuous time world. So that means that there is a certain mapping ratio between these two domains, which we will use. So we will come back to this. Okay, so this is sort of key importance. So let's see, just to sort of repair the thing I did last time. So we discussed about this unit circle, and then we had our accumulated transfer function like this. And on this unit circle where we are just on the stability limit, we have z equal to e to the j omega t. And then I said last time, if we take z to the minus 1, this was e to the minus j omega t. And that's approximately equal to, according to Taylor, 1 minus j omega t plus some ordo omega squared. And why is it, oh well, maybe I should say omega t squared. Omega t squared. I mean, this is a small number because we have already selected a small angle here on my unit circle. So this term is approximately 0 ordo, at least comparatively much smaller than this guy. Okay, so with that in mind, this we can translate into S. And then we can just insert this equation into that expression. So we have minus C1 divided by C2 times 1 over the 1 minus minus J ST, sorry. Was the so S times T here. And well, minuses disappear and minus 1 is 0. So for this we have that this is approximately equal to minus C1 divided by C2 1 over ST. And then this in turn we can write as minus 1 over SC2 times T divided by C1, like this. And this was our equivalent resistance. So this is now equal to minus 1 over SR equivalent times C2 from last week. So we didn't. So this is C2 and that's C1. And this switching happening here was the equivalent resistance. So that means if we look at this formula, it's very similar to the continuous time integrator. So if I draw this diagram, you will recognize that transfer function. A simple op-amp. So if this is V1 and this is V0, C2 and R equivalent. And obviously V0 divided by V1 is equal to minus 1 over SC2 R equivalent. So here you can see the mapping and the relationship between the two components. So as long as I fulfill the following requirement, then I'm sort of safe. Then this guy performs also a continuous time operation. Of course, we might need some filtering to filter out components here. This frequency domain will replicate itself if I measure with the spectrum analyzer on the output. I will also see some replicas of this happening around multiples of the FS. But typically we have a quite high attenuation due to this requirement. We have a quite high attenuation of those peaks anyway. But of course, I could add a very simple, maybe RC filter to further attenuate those guys. All right, so with that in mind, concludes the important things that we need for our next step here. So we're just going to build up towards the filter. And before we get to that, we just need to do one short observation. And so I'm just going to draw the diagram here again for my own sake, more or less. I'm just going to draw the diagram again. So we have a switch like this, and we have a capacitor, and we have a switch and ground, and then V1, V0, C0 plus C1. All right, so I could toggle these switches back and forth, and in this particular picture, I will not really care about which one is pointing where. I'm just sort of indicating that we do have options to, switching counter phase or not in our conditions here. We have 2 states for each switch. So I have 4 different ways of connecting this. So that means that this guy can also become minus C1 divided by C0 times 1 over 1 minus Z minus 1. That's one option. I can also create the function which is C1 divided by C0 times Z to the minus 1, 1 minus Z minus 1, etc., etc., dependent on the phase then, dependent on phi, more or less, the choice of where do I want to put these switches. Further on, it's quite easy to also perform addition. So I can pick this particular node. That's the key node to the whole enchilada. That's where I sum up all the currents. So if I just take another path here, like this, and connect another input, say V2, and yeah, C2 then. And then once again, we could play around with the capacitors here. Sorry, with the switches here. And then I get the quite nice way of just summing up the two signals. So for this, I get V0 equal to, say we pick this guy, C1 divided by C0, 1 over 1 minus Z minus 1, for example. And then I could pick the other one if I like, plus C2 divided by C0 times Z minus 1, like this. And then this then multiplies with V1, and this multiplies with V2. So it's quite easy, just the way we did with, the continuous time domain. We could add additional resistors at the input here to connect to another V2. We can obviously do the same here, but the nice thing is that I also have the option to change the sign and introduce delays, so I can play around. I'm a little bit more free in the way I can play around with the input connectors to this accumulator. So this is also something we're going to use later down the road. All right. So I think that is a good starting point. So this is actually a summing accumulator. So that's the one we're going to use. Now we enter the world of filter design. So let's start with the basics. So this is obviously analog filters first. And with analog, we mean continuous time and continuous amplitude. And then we're going to look at discrete time filters, which are then continuous in amplitude, but they are discrete in time. So you have probably a quite good idea what the filter is. So I'm not going to spend super duper much time, but we know that the filter typically does a selection, a band selection of our frequency domain. And filters are really important, so that's nothing we should really just throw away. Filters are integral parts of most sophisticated signal processing devices today. If they're not in the analog domain, we do have an AD converter or D to A converter, and then the filtering is done in the digital domain. But filters are key integral components for all designs, more or less. Think of modulation, when we have multiple bands of signals that we can place in different frequency domains, and then we just slice them out with different filters. In our case, we're going to look at low-pass filters. So we pass low frequencies through our filter. Why is that? Well, that's obviously due to this requirement. I mean, we have already restricted ourselves. Not only that the bandwidth should be much less than the sample frequency per se, we could have a more narrow band higher up in frequency, but this sync weighting will force us to limit ourselves to low pass domain. So we typically have a certain low pass characteristics so that we can limit ourselves to. And then obviously we can use the technique, but then it just requires a little bit more of thinking and playing around with clock frequencies, etc. All right, so this transfer function h of s, we can typically write in a sort of standardized way 1 plus A1S plus A2S squared plus blah, blah, blah. And then we have 1 plus B1S plus B2S squared plus blah, blah, blah. A standard way of writing a transfer function. We could also write this on Bode's normal form, but let's just start here. And then K is my level gain, if you like, DC gain. If I put S equal to 0, all these terms disappear and I get K times 1, etc. And I have an order of the polynomial in the numerator and denominator. I have certain requirements, obviously, for stability point of view. The order of the polygon also determines how many operational amplifiers you need, or accumulators, if you like. So in this particular case, with the 2 here, I wouldn't have to have 2 accumulators if the dots are not there. So, okay, so yeah, let's just state the obvious, perhaps. Y divided by X. So I imagine I have a black box like this. I have my Y and my X and my H of S here in the middle. That's my filter. I can reorder this. I can write Y of 1 plus B1S plus B2S squared plus blah, 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 blah. That's equal to K times the X times 1 plus A1S plus A2S squared plus blah, blah, blah. All right. Now I can rewrite this, and I'm not going to make it in too many steps. We will just sort of argue. I can pick this whole stuff and bring to the other side. So I can keep Y on this side, and I can keep obviously this part on the other side. I will also divide the expressions with S to the power of the highest level. So divide with S to the N or something like this. And if you like, you can read more about this in the PDFs, but we essentially get Y of S equal to something like maybe K of X, K times X, plus something like 1 over S times a alpha times X plus a beta times Y plus 1 over S, and then it just continues here, say alpha 1, beta 1, alpha 2, X plus beta 2, Y plus 1 over S, parenthesis, blah, 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 blah. And then I have a long story here. The important thing is, however, that we have to rewrite it with integrators. So 1 over S is an integrator. We already know that from the work we did here. That's an integrator. We get 1 over S something. And why do I want 1 over S? Or why couldn't I just stuck to this S thingy here? And why did I do this division? Well, S implies a derivative. And if you look at this in the terms of frequency domain, the S curve will point upwards for higher frequencies. So it will have high gain for high frequencies, which means it will amplify noise for higher frequencies. So typically 1 over S, the integrator has nicer properties because for higher frequencies, it's approximately 0. So I sort of damp any additional noise or problems I might have. So that means if you look at this, we can write the output signal as a linear combination of the input plus an integration of a feedback and also an multiplication of the input signal plus further integrators here. So this is a typical normal form or transposed normal form that you may find in the textbooks in the basic courses. But you typically, we just say that Y is equal to plus and an amplification of X like this, plus, and then I do have an integration, 1 over s, and then here I pick my another replica of x, and then I pick a replica of my output. So this is y, like this, and then it just continues more or less. So I can just take another replica of my input to my integrator, and another replica of the output, etc. And these are then my coefficients alpha and beta. We're not going to dig into the details here, but what you get is a signal flow chart. Okay, and that signal flow chart, it's quite easy because we just replace with the summation, the summing integrators that we have, like this. So we can then realize this flow chart. And once we have the flow chart in place, we just replace with our summing, inverting, and gain amplification, amplifying accumulator. So all these additions and multiplications and potential signs differences we can implement with SWITCAP. So basically, the original function, just go through blah, 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 the basics, find the signal flow chart, and then manipulate that to get our SWITCAP implementation. Okay. Just to put some aspect to that, we can just pick an example for in the continuous time domain. So to some degree, stating the obvious, but it's good to repeat. So say that h of s should be equal to the minus k 1 plus s over p1. So that's a first order filter with a single pole and a certain gain. Then we get that y of 1 plus s over p1 is equal to the minus kx. And I can multiply both sides with 1 over s, so I get, or p1 over s, so I get p1 over s y plus y is equal to minus p1k over s divided times x. And then I get that y is equal to minus p1k over s times x minus p1 over s times y. So in this particular case, we have equals 0 times x plus 1 over s brought out, and then we have p1k x plus p1 y, and then this should be a minus here. Okay, so that's the way I can take my original function and just do the manipulation, and then I should implement this like a flow chart. Yeah, so we have that y is then equal to p1k over s minus times the x and summed with, and then I have p1y minus divided by s, sorry, p1 over s, like this, and y. And then I can see that we can do certain manipulations. I can push my integration forward in the summation sign. That's essentially what we've done here when we brought out 1 over s from the parentheses. So, but I can also bring p1 divided together here. So I can write this as k times x, and then we have here just a gain of 1. And then here I can bring out minus p1 over s, and then brought out to y. All right, so just to, because we will do some of this manipulation shortly, so I just wanted to illustrate that you can find the common component here. Obviously, that's the very same thing as identifying common components inside this parenthesis, and then just push it forward in the flow chart here and bring it to this point. So that's a way that we will do later down the road in order to share as many resources as possible in our diagram. Okay, well, we sort of already perhaps know what the implementation will be here, but I have a summation and an integration. In this particular case, I have a summation with identical signs. So I could, in this particular case, I can quite quickly realize that this is equal to a standard summing amplifier like this. Oops, sorry, this should obviously not be there. It should be the ground. Like this, and this guy also connects to the output then. Okay, V0, V1, C0, R0, and R1. Okay, so just identifying from the flow chart, and then we take a reference implementation. And then we need to do one more thing before we're done. What do I know from this flow chart? I know that I have P1 times K as a sort of value, and I also have P1 in the other one. So I have two unknowns, P1 and K. But in this implementation, I have R0, R1, and C0 as unknown. So typically, in our system, you will have an overdefined system with too many variables or more variables than you will have sort of parameters that you have to calculate. So here there are two unknowns, or known probably from the spec point here then, K and P1. Here I have three unknowns, so you have to select something here. So that's also something we're going to do in the next hour. What can we do to sort of do this? Well, I obviously see that from V0 to the output, my transfer function is minus 1 over S C0 R0. C0 R0. Let's bring that to another page, sorry. Okay, so I will simply say that from V0 to V0, I have a transfer function which is minus 1 over S C0 R0. So what I do is I identify the path from V0 to V0. Like this, so. And then I do the same thing in the flow chart. So I would take the path from, in this case, Y to Y. So that's 1 times this stuff. So from the flow chart, I do have minus P1 over S. Okay, and then I have V1 to V0. Same thing, identify from V1 to V0. And then I can find, well, we know that already, 1 over S C1 R1. And in the flow chart, I should take from this point to that point. So K times this stuff. So that should equal minus K times P1 over S. All right. So I have a flow chart implementation giving me this, these two guys. Then I have my real circuit implementation giving me this equation set. And then we will look in SWITCAP. We will have a third level where we have mapped from continuous time to discrete time domain. But going through this will help you understand what we're doing next, or in the next hour. So obviously we just can identify part by part here. So these two should be equal. So I get one equation saying that this should be equal to that. Okay, obviously minuses disappear, the 1 over S disappears. So obviously P1 is equal to 1 over C0 R0. Yeah, that's coming from that equation set. This guy tells us that K times P1 equals to 1 over C1 R1, sorry, that should be naught, of course, C naught of R1. Yeah, and then we see that we have 2 equations, but we have 3 unknowns. So we can obviously multiply this with R naught divided by R1, R naught, sorry, just to extend that equation. And then we see we can identify P1, this expression in this part. And then we see that K is equal to R naught divided by R1, for example. But typically, you have to choose values over determined system. Is a key word here, because that will be very obvious shortly. Okay, so yeah, C naught gives us requirement, R naught we can choose, and given that choice, we can then select R1 accordingly. All right, it's 4 o'clock, so we're quite close to having a coffee break. I guess this compiles pretty well what we know about filters. Okay, so I've drawn a ladder filter, same as down here, in a slightly different format. We just made a Norton equivalent version, and here I use a Thevenin equivalent version. This is a little bit more symmetric the way it's drawn, so never mind. What we're going to do now is to construct a set of equations to describe the flowchart. And the flowchart, the purpose of the flowchart is to find a set of integrators. So either we could use this method that we used in the beginning, where we discussed a generic transfer function like this. We could do that also here, but one of the problems we have here is that there is a cascade of integrators, like down here. You have a set of integrators, which means that certain signals have to pass through the entire chain of integrators. So this structure has a certain sensitivity to potential errors in this long path. So this LC ladder network gives us shorter paths from input to output. And there is also a certain sort of spread across the whole filter. So a small error in one path is replicated and distributed to the entire chain, signal chain in your filter, which has some nice properties. A filter specialist would be able to explain that much more in detail than I can do. All right, so we introduce some currents into this diagram. So let me use another pen. So I'm simply going to add a current here. I'm going to call it I naught. I introduce a current here, which I call I2. And I introduce a current here, which I would call I4. And then we're obviously going to use KCL, might be obvious here. So the currents are the summation points, like they were for our accumulator or integrator. So I have a summation point here and a summation point here. So I just have to sort of bring this stuff together. This is my V in, of course, and V out is taken across this resistor. Assuming ground here, we see that V3 is the output. So if we like, V3 is V out here. Okay, so we can now formulate a set of equations. I'm going to get 5 equations here in the end. And then we're going to introduce something called state variables, and all of them will be voltages. Okay, so obviously I naught is equal to V in minus V1 divided by R naught. And now I'm just going to be a bit lazy, so I'm going to call that Y naught instead. Just to save ourselves some space. Okay, that's a current. That's also current, obviously. So I'm going to multiply this with a factor R to get the voltage. And R now is just a scaling factor. So that's going to add up to one additional variable that you can use in your design that you have to choose simply. All right, what else do I know? Well, I can introduce a current here through this capacitor. And then I know that the sum of those two currents will be equal to each other according to KCL. That means that 0 minus V in, or V1, sorry. So the voltage difference here in drawn in that direction is then equal to Z1 times I2 minus I naught, like that. And Z1, well, that's the impedance of this node here. So I'm going to shortly replace it with 1 over S, but just for now. Okay. What I can do here in order to get voltage variables. So here I have a voltage and here I have currents. So I would like to multiply them to get voltages. So I can just extend this with R over R, my scaling factor. And then this gives me now V1 is equal to Z1 times parenthesis Ri naught minus Ri2. So now I have one voltage state, 1, 2, 3, and yet another one, 4 there. Okay, and then we just continue down the chain. So I would get same pattern, Ri2, this current here. That's going to be equal to V1 minus V3 times Y2, this guy, but admittance, and then multiplied with R, V2R. So then I have another voltage state variable is equal to difference between two state variables, V1 and V3, and then some scaling factor Y2R, or indeed an integration. And then we have V3 is now equal to Z3, this guy, times I2 minus I4. I'm using this pattern at the moment then. Okay, and then I multiply with R divided by R. So I can just R times R, and the observant sees that I forgot this divide by R here. So we should divide by R here too. So that's the pattern giving me V1 situation is obviously identical to the V3 situation in terms of sort of structure. And then we take the last one, I4. That should be I4R4, by the way. Okay, and that's, yeah, quite simple. We just get Y4 times V3. And the minus, so the current going this way is, sorry, plus V3 times I4. And then I need to extend with an R to get voltages everywhere. I4 times R times V3. Okay, so that's the idea. So I'm just basic KCL, but rather than having current, I want equations that are always voltages. And then I use these voltages as state variables, as sort of observable voltages in my network. So I have one guy here, and I have a new one here, and then V3, and eventually R times Y4. So 1, 2, 3, 4, 5, 6. And then V in is obviously a known input. So, and then you see that things sort of hook into each other. Ri2 is a function of V1 and V3, but Ri2 is also a function of V1, so there's a sort of feedback going on here. V3 includes the Y2 and Y4, etc., etc. So there's a certain pattern going on here. So based on those equations, it's actually quite easy to formulate the flowchart. So obviously one could, just for the sake of the lab, take the template and work from there. But obviously the purpose of the lecture is to show how you can do this for any order of your filter. So we're doing for a third order filter in the lab and also in this example. But obviously you can extend this to a fifth order or a seventh order or second or fourth order filter. It's as easy as this, more or less. All right, so yeah, essentially I just have to look for my equations here now. So I can take my V in. So I'm just looking at these equations. V in minus V1 plus, and then I add an inversion, minus 1. Okay, so that's V in minus V1. So here I have V1. And then I just multiply with Y naught R, and we will know what Y naught is. That's the inverse of R naught. So this is R divided by R naught, like this. Okay, so that gives me this guy, Ri naught. So down here I have Ri naught. Okay, next one, V1 equals the sum of two guys multiplied by something. So V1 is going to be equal to the sum of two variables, Ri naught and minus Ri2. So this is also going to be multiplied by minus 1. And then I have Ri2. And then I multiply with Z1R, but Z1 is equal to 1 over the SC1. So this guy here is going to be 1 over SC1R, this term. And then I have created V1. And then we look at Ri2 here. It's going to be a multiplied summation of V1 and V3. So V1 we just pick here, and we sum that with a minus 1 version of V3. And then I take that output and multiply with Y2R. Y2 is the admittance of the inductor, so Y2 then is equal to 1 over the SL2. So this is going to be yet an integration, and that's going to be R divided by SL2. And then we can just continue here. So I will get a summation, and then I will get a minus 1, and this will be yet an integration. So 1 over SC3R, and here in the final step towards the end here, we will have R4 divided by R in the end. R4 divided by R. So a pretty neat way, and you see I just sort of knew what's going to happen here. You just cascade them after each other. And you see that there are sort of big loops here where the signal goes back and forth through the entire network. Something happening here goes all the way this way, back here, and then fed back. So we have a sort of distributing everything throughout the entire network. Okay. We can do some fixes here with respect to the signs. We have a minus here, for example. If we remember from our continuous time integrator, it would be nice to see a minus here in a transfer function for an RC integrator. So what I can do is simply add 2 minus 1s here. And then I can do that action that we discussed previously, that I can push things back and forth in my network. So I can take those 2 minus 1s and bring into this integrator instead and bypass those. And then I have a minus and a minus here. I could, depending on what I want to do, I could either bring those minuses here, or I could introduce minuses down here and bring them back. So we're actually going to do that. I'm going to add a minus down here. And we have a minus, and a minus and a minus. So all these minuses are taken away from the equation. Sorry. So I can get rid of 4 minuses here. And I have 1 minus there and a minus there. And these 2 guys I can push into this guy. So minus here. Like this. So it's a quite neat way of getting rid of everything. So the only remaining thing is this guy, which does not have a minus. So I do have 2 inverting integrators here, but I lack 1 here. But we know from our background in preschool that we can invert a signal quite easily by just connecting 2 resistors in series like this, and then I get an inverting amplifier. So if I do need a minus here, minus 1, and then a minus here, then I can implement that minus with this guy. So if you look at this, this is 1, 2 resistors coming in here, and then an integration with C. That's what implements all these 3 guys. So 1 here, 1 there, and 1 there. We will do 1 slight modification, and that's this guy over here, because here we don't have any integration happening. So one can move this guy down to this adder instead. So if I multiply V in with R0 divided by R and bring it to this node instead, like this, and multiply that with R divided by R0 V in, then I can also get rid of this summation happening here. So I just push forward and bring back through the network. Right, so that's essentially what's been done in these diagrams. So rather than drawing that, I'm just going to bring that forward. So let's bring that down a bit. So, and then here. So that's the flow chart that we did. Right now on our paper. So we do still have the positive integrator in the middle. And then let's look at the reference filter. Sorry, I have the wrong file open. I thought I would save some time, but it's not there. Okay. Anyway, so let's bring that back again. Okay, what I wanted to show was simply the implementation with RC components. They are somewhere there in the PDF material. So essentially the network, but we replace with our circuit implementations instead. All right, so let's just discuss how we get further down to SweetCap. So if I did have time here, I would have shown, so see PDF for implementation. Okay, or maybe we should just, so essentially what we see, the three integrators, so we find them also in the schematic, but we have the three. So this is the first one, and that's the second one, and that's the third one. And then we have to do an integration, sorry, inversion with this -1 using this inverting buffer. And the addition is done through the resistors. So R divided by R naught is implemented by this R5 down in the corner. And also the insertion of the input voltage to the system is done through one additional resistor down to this additional node here, etc. So it's pretty straightforward, I would say. Okay, so let's look at how to get to SWITCAP with this. And then we need to do a slight discussion on how to get to SWITCAP. Okay, so it's about getting from continuous time to discrete time. And of course, today you have computer tools. You can easily open MATLAB, and there are toolboxes in MATLAB that more or less gives you a number directly. You just specify what frequencies you want, what sample frequency you have, etc. And then it pops out some values for you to use. What we need to do is to do some transform. So you need to transform from S to omega t. And in this particular course and lab, you will use the Ldi transform. So that's the lossless discrete time integrator. Ldi. And that gives us a relationship between the two frequency domains in the following manner. So S equal to S naught times Z minus 1 divided by Z to the minus half. So I'm going to replace all my S's here with this expression. So S naught is a scaling factor, and that's just a choice on your frequency domain. One can quite easily, here we have Z minus 1, I can break out Z to the minus, I mean this expression here I can write in the following manner. Z to the half minus Z to the minus half, plus I guess minus, something like that. And etc. etc. I can divide with a factor 2j. I also know that Z is equal to the ej omega t on the unit circle here. And then you see here we have Euler's formula, so I can rewrite this expression as a sine if I like. And if we do that simple maths, I'm not going to do it here, but we see that omega a is equal to 2s naught sine omega t divided by 2. Or if we like, the scaling factor s naught is equal to omega a divided by 2 sine omega t half. That you can convince yourself quite easily here if you just go into this equation and do the Euler formula, etc. the half, omega t half, etc., etc. And then omega A is a frequency on your continuous time domain, and omega t is the angle. So you just decide how you want to scale your system. So that's part of the lab, obviously, too, then. So I do have my frequency axis. Let's repeat that while we're here. So I do have some frequency axis like this, which maps on my unit circle like this. So I know I have a certain angle here, omega t. That's going to map on my omega axis in my continuous time domain and my discrete time domain. So you just have to select something, my angle being omega t. Here, my angle in my discrete time domain has to represent a certain frequency in my frequency domain. Okay, so this is, invent the number omega a here, minus omega a. So those two guys have to map on your selection of this angle on your unit circle. So it's up to you as a designer. Essentially, we can also look at this figure. If you remember from the first half of this session today, we said that we had to limit ourselves down here somewhere. So in the discrete time domain, this corresponds to this omega t angle. Let's call it omega t naught, for example. So that particular angle in the discrete time domain corresponds to omega t naught. And that then also represents your omega a here in your analog domain. So that's quite important, because if you think about it, if you change the sample frequency, you will change the characteristics of your system. So that's why we have to pick this scaling factor, so that I know that 1 kilohertz, for example, corresponds to an angle of, for example, pi 20th or whatever. So I need to sort of lock these two guys against each other. Otherwise, the system doesn't know how you sort of stretch this circle if you change t. If you go from 1 gigahertz to 2 gigahertz, what's the impact on the, what does that correspond to in the continuous time domain? So that's handled by this equation then. S naught being equal to your chosen frequency, omega a. That's chosen. And that's also your chosen angle. And also here then, the angle cannot be too high. I mean, we need to have an angle which is much less than pi, according to this discussion about sync. So omega t is much less than pi. So that's an effect of omega a being much, much less than 2 pi fs then. Okay, so with the transformation also comes a certain choice. So that's a choice you have to do in the lab. That particular scaling factor. All right, and you see it's not linear. It's a sort of strange equation here. So for example, if you choose to double your sample frequency, and if you maintain the S naught, that will have some nonlinear impact of what that frequency corresponds to in the continuous time domain. So beware here a bit of your choice and how you implement that. All right, so essentially we're pretty close to the end result. We have to do a couple of things before we finalize, and maybe I'm thinking maybe we should just bring in I think we should save ourselves some drawing actually, so I'll bring in my PDF document instead. Okay. So let's start here. So, well, let's start from the Okay, so this is the flow chart we had that we calculated before. And what the Ldi transform now tells us is to replace the S's with this S naught times blah, 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 Z to the blah, blah, blah. Okay, so that's what we're doing. We simply do that straight out of the box. Okay, so all the S's now were replaced with S naught parameter, so that's a scaling factor, yet a scaling factor in your design. And then we replace S with this Z to the minus half thingy. So we're quite close to the accumulator expressions we had from the first hour or in last lecture, but we find a half in the numerator. So we have to get rid of this half somehow. And how do we do that? Well, we take our trick to push a half through the system, flowchart system. So I can imagine I have a half factor in front of this amplifier and I just push it forward or backwards. And then I can push it back and forth through the network. So I see I can push a half out to this branch. I can push a half into that branch and get Z to the minus 1 instead. And then here I can push the half out to that branch. So the resulting situation is this. So pushing the halves to these branches and then combining them to the following system. Okay, so I have now my integrator or accumulator that we recognize from the first hour, one of them with the switches in a certain position and the minus. And then we have the other one that I was referring to with the delay and no minus. The other version of just flipping the switches back and forth. So you just move the switches accordingly. All right, and then we have the last one with the minus. So this sort of implies that I can just select very same type of accumulator and then I just switch or toggle the switches accordingly to get the sign and the Z to the minus 1 delay. We're going to talk about this half in a minute. We're just going to finalize the PDFs here. So if I go down here, just to show you the resulting circuit, essentially this guy. So not too complicated, to be honest. It looks pretty straightforward. So I just taken my accumulator with a fixed capacitor across here with a certain C7. And then I have 3 inputs, C5, C4, and C6. And they are then switched accordingly. Notice also I can use the switch to switch 2 caps here connected this way. I could also push the switch forward if I like to and have replicas of the switches in the C6 branch and C11 branch, but switch sharing is quite useful, so we can move it. Also here we would have originally one switch in the C8 path and one in the C9 path, but we can combine them and push them forward into the C10 path here. And yeah, if you study the switches here, you see that this switch on the C7 path is connected like this in the original phase, but connected like this in the C10 path. And then at the input, we do the same thing. We just alter the switch position from the original pointing towards the input. I swap it to point towards ground initially, and then I get the half for free, half clock cycle delay. And that implies yeah, that we can also get rid of this half down here. All right, so let's just look at what's happening on the sides here. How can we get rid of these halves that I accumulated and pushed forward in the network? So let's just spend a minute on that. So let's get rid of this. So you see there's also already indicated a certain solution to the right there in my picture, but so it's not too complicated actually. Okay, so I pushed a half through my system, and then I have R divided by R naught times Z to the minus half. But then I know from the Ldi transform that we had here, I do have Z to the minus half already in the denominator. So I can use this, or in fact, I can combine this and solve that equation. So we have S equal to S naught times Z to the minus 1 divided by Z to the half. Should be plus half, of course. Z to the half. And yeah, this is a second order equation. I mean, let x be equal to Z to the half. And then we have S divided by S naught times X is equal to X squared minus 1. And then I have X squared minus S divided by S naught times X plus minus 1, sorry, equal to 0. And that should be plus. And then I have X equal to a half S divided by 2 S naught plus minus the square root of 1 minus like this. Okay, and then I can write this as x being equal to j omega divided by 2 S naught plus minus the square root of something S divided by 2 S naught. The details are not super interesting at the moment. We will wrap this up and yeah, do some rounding more or less. The important thing, however, is that I see that my Z to the half here, it can be written like a complex number plus a real number. One of them can be omitted from the discussion, the minus. And then I get, you know, from this, I get something like R divided by R naught times the first factor j omega divided by 2S naught. And sorry, we should have 1 over here too, like this. So plus the square root of 1 minus S divided by 2S naught squared. Like this. X was to the half here. We should multiply with minus half, so 1 over. Anyway, I'm adding these steps just for information. So there are some tools later down in MATLAB in the lab for you. But it's good to know what's happening here and why one does it. So essentially what this is saying is that the original resistor I had on the edges, if you remember from the filter here, I have R0 and R4 on the sides. And then I pushed the Z half through the system. I can bring the Z half from the Ldi transform. I can solve a second order equation to find what Z to the minus half is. That's equal to this expression somehow. That implies that this R is in fact, or this product is a resistor in parallel with a capacitor. So these two guys are equivalent, more or less. So they are equivalent with a capacitor, CL, which is given by this factor here. And then there is also a frequency-dependent variable here. It's minus because we have j omega. I'm a bit sloppy here. So that should be omega, and j squared is minus. And then I have a frequency-dependent resistor here, R times omega. That's a fact due to this the pushing of Z to the half through the system. So ZL pops up and R of omega becomes frequency dependent. But once again, the motivation is that we're looking at a very narrow band in our circle here, so we can assume that this frequency dependence is more or less unity, so we don't really see that dependency. So this in turn then is approximately equal to a capacitor in parallel with a resistance then. So I'll let you do this calculations if you want to study that in detail, but the key sort of result here is that the multiplication of this time factor gives us a equivalent circuit of being a resistor in parallel with a C. And then if we go back to the original schematic, this guy shows up here as being in parallel with C1 and C3. So this resistor then, due to this Z half insertion, will give us an additional capacitance here and an additional capacitance here, C1 prim and C3 prim. So from a design point of view, that just implies that this C1 changes a little bit and C3 changes a little bit. Otherwise, the structure is the same. So going back to the PDF here to explain that or show that. So here is the thing I was talking about. The resistor times the Z to the minus half is replaced with a parallel coupling. And then we get the C in parallel. And then indicated here in the schematic is done C1 prim as a sort of modified capacitance on both sides. So both C3 and C1 are affected. So you do have to change this slightly, and the formulas are given down here then. So that explains that. And then the final step is to identify all the paths. And yeah, I think this is pretty self-explanatory actually. But you can just write down all the paths you have from, in this particular case, from input to the voltage V1. That gives me a certain multiplication in my SC filter domain. C4 divided by C7, blah, blah, blah. And then I have the signal flow chart, and then I combine them just like we did in the first hour. And that gives me a relationship between C4, C7 and this flow chart number, which is from our reference filter, and etc., etc. So you get all these kind of equations by investigating the different paths from one voltage to another voltage in the state diagram. And then it's up to you to do the assumptions. For example, you can assume that the resistors are equally large or something. Or you can assume that all capacitors connected across the op-amps might be equally large. Could be an assumption. So C7, C10, and C13, maybe you want to make them all equally large, for example. Okay, so that's essentially it. It's pretty well explained in the PDFs, even though I couldn't find them before in a swiftly manner. But if you do some searching, you will find quite a few different tutorials on how to go from reference filter to SWITCAP implementation. And then just one final comment. We're already a bit close to the break here, but you also need to scale your filter. So I'm just going to add here. Why do you need to scale your filter? Well, that's because now once you insert your operational amplifiers into your design, you are sensitive to the voltage swing. First of all, you have a 1 volt supply or 1.2 volt supply, and a certain input level coming in on the input signal down here to the left. So say you have 1 volt here, for example, what's the implication on the voltage level of X1 at the output of this op-amp? It's a bit hard to say, we don't really know actually. So you have to investigate so you're not clipping the amplifier. So maybe, you know, maybe you have 1 volt here and this guy tries to amplify to 2 volts. Then obviously it won't work. So you have to scale down your input signal. So that you can do, for example, by just, you know, reducing or increasing C4. That will amplify the entire network because that amplifies directly the input signal. So that's quite low-hanging fruit. However, you also have the issue that you might have too high swings propagating through the network. So say you have a certain swing on the output of the first amplifier X1 here, and then that's too high or too low before you throw it to the next amplifier C10. Yeah, then the strategy is to cut the network according to any electrical principle. If you cut one wire, you have to cut another one. So I'm looking at an intersection here between C6 and C8. So if I look at the paths going out from the intersection and all the paths going in from the intersection, if I scale them accordingly, so I scale up the output and scale down the input, then my global system function is untouched. So that's a sort of simple way of doing it, or it can quite easily be understood. But so I scale up with a factor K2 and then I scale down with a factor K2, whatever's coming back. So then I can scale up to a certain proper limit. So I don't clip X2, or vice versa. I might want to increase the signal even in order to get better linearity or something. And then I can just continue. Maybe I want higher swing at the output. Okay, then I put another intersection and scale C9 and C11 with factors K3 then. So all the guys going out, I scale up, and all the guys going in, I scale down. So it's a quite simple principle. I don't think we need to do any calculations here. So, all right, it's 5 o'clock.